I should also say that the news yesterday was that this object came closest to the sun, and it received a huge amount of heat from the sun.
Mm-hmm.
And the latest report indicates that it became extremely bright, much more than expected for familiar comets. This morning, we have a report that the object got much brighter than expected, and moreover, the color of the object is blue, bluer than the sun. And that's very surprising because usually when there is dust around an object, it should make it red.
Something extraordinary has just unfolded in the silent depths of space. A traveler from beyond our solar system, designated 3I Atlas, has entered our cosmic neighborhood, and what we've learned about it is nothing short of astonishing. The James Webb Space Telescope, with its unmatched infrared gaze, has turned its instruments toward this visitor and discovered something no one expected. Strange lights, unfamiliar emissions, and behaviors that defy the patterns of any known comet. What was supposed to be an ordinary observation has become a window into a deeper cosmic mystery, one that could change how we define comets, interstellar objects, and perhaps even the boundaries of what we believe is possible. When the James Webb Space Telescope, or JWST, focused its near-infrared spectrograph on 3I Atlas on August 6, 2025, the data that streamed back immediately revealed anomalies. The object's coma, the luminous envelope of gas and dust surrounding its icy nucleus, glowed with an intensity and color unlike any previously recorded. Its spectrum was dominated by carbon dioxide, vastly outshining the levels seen in normal comets, while water vapor was curiously faint. The term mysterious lights in this context doesn't refer to visible flashes, but to unexpected infrared signatures, glows, and energy emissions that resist conventional explanation. Ordinary comets, as they near the sun, behave predictably. Solar heat vaporizes their ices, jets of gas and dust stream into space, and the familiar tails form. But 3I Atlas isn't playing by those rules. Its orbit is hyperbolic, confirming that it comes from beyond our solar system. It's only the third confirmed interstellar object ever observed, after Oumuamua and 2I Borisov. Every photon it emits, every molecule it sheds, carries clues about the distant environment it came from, an environment that could be unimaginably different from our own. What makes these lights so compelling is that they may not come from sunlight alone. Some researchers propose that there are internal sources of heat or chemical reactions at work, perhaps even reflections from surfaces unlike any we've seen before. A few have gone further, suggesting, though with extreme caution, that there might be technological origins behind these emissions. Such ideas remain highly speculative, but the data itself demands attention. JWST detected CO2 outgassing at unprecedented levels, coupled with an unusual suppression of water vapor, suggesting physical and chemical processes that are rare in our solar system's comets. The lights appear as concentrated glows within the coma, sometimes even near what seems to be the nucleus itself, as if the object's interior were alive with activity. Infrared mapping shows scattered light around 1.2 micrometers, highlighting dust, and bright emission lines from carbon dioxide at 4.3, water at 2.7, and carbon monoxide near 4.7 micrometers. These wavelengths correspond to energetic activity, implying that 3I Atlas isn't just a frozen relic, but a dynamic, active body with internal complexity. The images even suggest bright zones, possible hotspots, or jets, punctuating the otherwise diffuse halo. One of the most remarkable findings is the sheer ratio of carbon dioxide to water. JWST's instruments recorded one of the highest CO2 to H2O ratios ever measured in any cometary body. Typically, comets from our solar system are rich in water vapor because water ice is their primary volatile substance. But 3I Atlas defies that norm, showing little water, yet abundant carbon dioxide. This imbalance suggests it may have formed under vastly colder or more radiation-exposed conditions than anything within our own planetary nursery. Hubble and ground-based telescopes added further intrigue. detecting unexpected traces of nickel and cyanide, materials found in comets, yes, but not in these proportions or with such peculiar emissions. Together, these compounds might contribute to the strange glow seen by Webb, hinting at internal reactions or exotic surface chemistry. But why does it matter? Because these lights aren't just an astronomical curiosity, they are a cosmic message. Every emission, every glimmer in that coma, is a clue to how other star systems form planets, store ices, and preserve their chemical past. If 3I Atlas originated in a protoplanetary disk around another star, then its chemistry is a record of that alien birthplace. The fact that we can see active emissions at all means its materials are still reacting, still alive to the heat of our sun after eons drifting through interstellar space. That activity tells us that distant ices and volatile compounds can survive the journey between stars. The unusually high CO2 level suggests that it was born beyond the carbon dioxide ice line of its home system, a region so cold that CO2 could freeze solid while water remained vapor. Such an origin would mean its chemistry was shaped in a frozen environment, with different exposure to radiation, dust, and stellar winds than what shaped our comets. Perhaps, over countless millennia, cosmic rays stripped away its surface water ice, leaving CO2 trapped deeper inside. Now, as it warms under our sun, that ancient carbon dioxide awakens, venting in luminous streams that glimmer in JWST's view. Its journey through interstellar space has also left its mark. 3I Atlas has likely spent millions of years exposed to cosmic radiation, stellar winds, and collisions with interstellar dust. Those encounters could have sculpted its crust, altered its chemistry, or buried hidden layers beneath. The lights we now see might be the visible result of that long journey. Heat emerging from within, gases venting from cracks formed by eons of stress. If water was lost ages ago, then what we're witnessing is the awakening of deeper, more exotic volatiles, signs of activity that differ profoundly from anything we've known. This challenges long-held assumptions about the lifespans of icy bodies. If 3I Atlas is truly older than our solar system, as some models propose, its sustained activity means that interstellar comets can remain chemically active for billions of years. They may not be inert fossils, but enduring messengers carrying the chemistry of ancient stars. That revelation reshapes how we think about the preservation of volatiles and the endurance of small bodies traveling between worlds. On a broader scale, this discovery opens a profound question. How many such visitors pass through our solar system unnoticed? If 3I Atlas is this unusual, how many others have come and gone, invisible to us? The lights seen within it are not just beautiful. They're reminders that interstellar space is full of wanderers carrying unknown histories. We may need to redefine our categories. Comet may no longer be enough. These interstellar bodies, forged in alien conditions, might represent a broader class of cosmic travelers, objects that are chemically and structurally distinct from anything that formed here. The implications ripple outward into planetary science and exoplanetary research. If 3I Atlas formed in another system, then its composition, especially its CO2-rich chemistry, might tell us how planets formed there. In our own solar system, water-bearing comets are thought to have delivered volatiles to the young Earth. But in another system, where CO2 dominates, the story of planetary development might have followed a different path. In a sense, the lights shining within 3I Atlas are the living signatures of those alien building blocks, matter forged around another star, now passing through our sky. JWST's observations also allow scientists to probe deeper into the structure of the object. The way light spreads through its coma, the variations in brightness, and the specific wavelengths of emission all provide clues about how porous the nucleus is, how its layers of dust and ice are arranged, and how heat moves through it. If those lights come from subsurface heating or jets venting from interior cavities, it suggests the comet's core retains thermal gradients, warm inner regions insulated by dust and crust, capable of sustaining activity even after a billion-year journey. Such resilience implies that interstellar small bodies are far tougher and more complex than we once believed. While 3I Atlas poses no danger to Earth, it will pass safely with a perihelion of about 1.4 astronomical units and a closest approach of roughly 1.8. The object's strange behavior underscores how unpredictable interstellar visitors can be. Future missions to intercept such bodies will need to prepare for surprises. Compositions we've never encountered, energies we don't fully understand, and lights that reveal internal mysteries rather than surface reflections. Time is short. 3I Atlas is already on its way back out into the dark, and every observation counts. From an astrophysical perspective, these lights reaffirm the transformative power of modern telescopes. Once, comets could only be studied up close by spacecraft or from afar through Earth's atmosphere. Now, with space-based observatories like JWST and Hubble, we could dissect their chemical makeup across vast distances with unprecedented clarity. In the faint glow of 3I Atlas, we see not just an object, but an entire history. Bright emissions from its interior, high-energy processes at work, and volatile materials behaving in ways no comet should. Some scientists suggest that 3I Atlas may be billions of years older than our solar system. If that's true, then its luminous emissions are like the light from an ancient relic, signals preserved from an era before the sun was born. Its composition, shaped in long-vanished star-forming regions, may contain the fingerprints of primordial chemistry, altered by cosmic radiation over epochs. To study it is to look into a time capsule of galactic history, a messenger from the galaxy's deep past. And yet, even as the consensus holds that 3I Atlas is a natural object, the unusual qualities of its lights invite deeper inquiry. Scientists are exploring whether hidden heat sources, layered ice structures, radiation processing, or other unknown mechanisms might explain the anomaly. Some have cautiously discussed the possibility of technosignatures, artificial signals left by advanced civilizations. But such speculation remains on the fringe, constrained by evidence. Still, the very fact that the data provokes such questions speaks to the wonder it inspires. Whether natural or not, 3I Atlas has expanded our sense of what can exist between stars. The discovery of its mysterious lights marks a milestone in the story of our exploration. This single object challenges everything we thought we understood about comets, small bodies, and interstellar chemistry. It hints at exotic materials, unknown internal structures, and ancient processes preserved across light years. More than that, it reminds us of the quiet power of our instruments, the ability of modern telescopes to detect the faintest whispers of energy from across space, transforming them into knowledge. Those lights, silent, spectral, and haunting, speak volumes. They reveal that 3I Atlas is not a dead fragment of ice, but a living witness to cosmic evolution. They map the places where gases escape, where internal heat stirs, where dust and ice mix in delicate layers. Their uneven glow suggests fractures and jets, channels through which the object breathes as it approaches the sun. The concentrated brightness in certain directions points to anisotropy, patches where crust has cracked, releasing stored volatiles in brilliant plumes. In a very real sense, those lights are the comet's heartbeat. The infrared maps captured by JWST confirm it. Emissions align strongly with carbon dioxide, near 4.3 micrometers, water vapor at about 2.7, and carbon monoxide, near 4.7. Dust scattering dominates near 1.2 micrometers. The CO2 signal, far stronger than the rest, identifies the glowing regions as centers of volatile escape, streams of gas turning sunlight into radiant chemistry. This CO2 dominance may reflect either its frozen birthplace near the carbon dioxide ice line or the result of long-term exposure to cosmic radiation that transformed other compounds into CO2 over time. Either way, the light is a chemical fingerprint, proof of active transformation under solar heat. Interestingly, the brightness is not uniform. JWST's mapping shows stronger outgassing on the sun-facing side, with concentrated glows where solar heating is most intense. That asymmetry reveals the physics of its surface: uneven layers, buried ice pockets, and fractures that focus activity along certain axes. The lights, in other words, outline the object's internal geography, its hidden vents, cracks, and conduits. Perhaps most striking of all, 3I Atlas was already highly active even while it was still more than 3 astronomical units from the Sun, far beyond the region where water ice usually begins to sublimate. That means these lights are driven by more volatile compounds like CO2 and CO, which can vaporize at much lower temperatures. This early awakening suggests that deep freeze volatiles remain intact inside the object, preserved since its formation in another star's cold cradle. The brightness we now see is their final release. If its outer layers are indeed rich in CO2 and poor in water, then 3I Atlas is a time capsule of its birth environment, a record of chemistry and temperature conditions long gone. Volatiles freeze at specific distances from their stars. Thus, this composition tells us that it was forged in a zone of deep cold, beyond even the water frost line. The lights, therefore, are more than a spectacle. They are historical documents written in radiation and dust. They tell us where this object came from, how it evolved, and what processes still animate it today. The fact that these volatiles have survived despite millions of years of interstellar exposure speaks to the durability of such bodies. The cosmic rays, stellar winds, and collisions that scarred its surface did not erase its ability to glow. Instead, they created layers of chemistry that now interact in vivid ways. The lights we see are both signs of life within and scars of everything endured. Even the dust plays a role. The glow is not entirely from gas. It also includes light scattered by dust and infrared radiation from heated grains. In some images, the dust halo is brighter than models predict, likely due to fresh dust lifted from vents and illuminated as it expands outward. The mysterious lights, then, are a conversation between dust, gas, and sunlight, a symphony of chemistry and reflection played across billions of kilometers. Recent studies suggest that cosmic rays may have altered its surface, transforming carbon monoxide into carbon dioxide and producing organic-rich crusts meters deep. That means the bright emissions might not be revealing pristine interior ice, but processed layers sculpted by radiation over millennia. In that sense, the lights are not just signals of current activity, but echoes of an ancient journey, a living record of everything that has ever touched this traveler.